Alright, mud fossil research has found that rocks have veins and arteries in them. They literally have veins and arteries in them. And you can go out and find these right in your backyard. And they all have veins and arteries. You see that? That the black is a vein and the clear or the red or the hole, in this case it's a hole, that's the arterial side, and they blow out. The veins have clamps and they don't blow out. So we're going to go over all these things. Now these have been DNA tests. That's been DNA tests. It's a human finger, and it's huge. And the same thing. This came off of the same hand. That's another fingertip. This has been CAT scan. It's 100% human. There's no question about it. And that's where the tendons invest and makes your finger go up and down and articulate. So this is what it is. And there's no question whatsoever about it. There's been 7 CAT scans, 3 DNA tests. This is a human lung. This has been DNA tested. 100% human lung. And that's where the blood invests at the bottom. There's a flap that invests at the fascia and holds it. This is the actual articulation of the pleura, which is the fabric that wraps the lung. Here's another lung that's been partially deteriorated, and that is the pleura, has eroded away, and that is the bloody flesh underneath. And if that was wetted, it will turn red. They rehydrate, and this will rehydrate in a second too. Here's another one that will rehydrate into a red, and that will turn red as well. It's been totally verified and authenticated. 3 DNA tests, 7 CAT scans. It's time that this has to be looked at in a very serious light, and I'm going to show you why. And I'll show you the chemistry behind it. I'll show you everything about it right now. Alright, by the way, if you don't know about mud fossils yet, it's really changed science dramatically. And I've opened up a Mudfossil University on YouTube. There's no charge for it. It's really not much of a university. It's just nothing more than YouTube videos that explain my understanding of what we are led to believe, and it's not real. Literally nothing that is theoretical is correct, because it's based on non-living dirt and dust and things that just glob together and they just live on a big rock and nothing matters, and it's not true. All the things that were in history were literally true. These things about the earth being alive and about planets and all that. It's crazy, but it's true. So you come here, the first one you should do is part 1, Mud Fossils Part 1, explains the chemistry. But I'm going to go a little deeper into the chemistry right now. Alright, what I want you to look at is the architecture of these little patterns. Now this is not a product of sedimentation. Now let's back it out here. Do you see the transition between this material, and then you get this fibrous looking material coming out of it? Let's back it out of here. You see what we have here? Now this was sent to me off the internet. I don't know exactly by who, but this is a structure in the Midwest or the out west of the United States. I'm almost certain. And you can find these all over the place. Now, if you look in the front here, these are little blood. That's a little tiny blood vessel of. This is fibrous material, which is muscle, and I have the same structure here in my mud fossils. Here's one right here that I have in my little lab here. Hold on one second. Alright, this right here is the same stuff. No question, it's the same identical architecture, and that is muscle wrapped around a bone ball. Now look at it carefully. You can see the fibers. You see all the individual fibers, and you see the straps running around it. Now, I'm going to back this out of here and turn that over, and that is a bone ball from a hand that was found. I'm going to turn this right over. It's tendinous material all wrapped around it, and here's the bone ball on the other side, which has eroded away. You know what, this would probably be better if I just hold it up in front here. Let me get a light. And let me back this out a little bit. Alright. That is the bone ball, you see it? And that is all the tendinous strapping material. And that is the strap of the tendon that runs down. And I have all the anatomical pictures of that. And that is what I just showed you, that the muscle fibers. And that is the size of the bone ball, and it's all eroded away. Now, this was found with a hand, the complete palm, and some other fingers, and they've been DNA tested and CAT scanned, and there's no question what they are. Now, that is the tendinous material, and you see the difference in material? Look at this carefully. You see the muddy, well, you probably saw it better in the microscopic shot, but let's look at this, if you can see this. That is a white calcium material. It's the connective tissue inside your tendons. And this muddy stuff, the little brown stuff, that's your actually fleshy muscular stuff. There's another giant piece of a muscle somebody sent me. It's in a park somewhere, and obviously that's a muscle. It's another shot of the giant muscle. This white stuff here, that's where it transitions between the connective tissue into the muscular tissue. And it's a muscle mountain. And the whole earth is made of giant creatures. This is a car way down here, a back of a car. That is a giant muscle mountain. This is similar to the kind of tissues we're dealing with. Now, this is really important to understand, is that these are muscle fibers, electron scanning microscope. And you see the different colors? Well, that means there's different metals in there, different minerals, and those different fibers have different chemistry, which means they have different tensile strengths and different properties that create this fiber that we live in, and that is just phenomenal, and it literally is what the world is made of. All right, look at this carefully. This is tendinous fibers, and they have this wavy pattern, and that's why they can stretch and pull. And these are the little black investment layers that are the bloody layers that service these different types of tissue. And you can see there's little fibers running through here. Now, they look all red and whitish looking here, but let me show you what they look like when they petrify in blood. All right, that same wavy pattern I just showed you, this is what happens when it petrifies in blood. These are the little investment layers that we saw before, those little holes that give it the blood. But when it soaks in blood, the transition metals are able to take on and give away every kind of molecule until they get exactly what they want. And that is what happens when they soak in blood. Transition metals is the key to everything here. And the reason that these take on these spectacular colors is because they are able to bond with exactly the partner that they want, because it is, I believe it's called nucleophilic reactions. They can grab one guy and say, well, you're not really working out for me, I want to get to this yellow color, and it'll eventually get to that yellow color because it'll find somebody in that blood, because blood has everything. All right, I either showed you or I will show you that all rocks have veins and arteries. Now, you see that? That's an artery because it's got some redness to it. You see that? That's a vein because it's got blackness to it. The black is a vein, and it's a FeO2 blood, and that's the FeO3 as additional oxygen. So, and that services this, which is a tendon. And this tendon has these, which are the fibrils in the tendon, which are calcified, mineralized tendinous material, which strengthens and so are these little ones too. There's a whole batch of different sizes, but this particular tendon was primarily, I believe, was in a more or less of a geological thermal area, slightly, but not boiled out, because they will turn into selenite actually when they're boiled out completely. And I have examples of that, and I have actually made that in the lab. But this olivine, and this is the tendinous fibers, and I show that a little later, or I have shown it already, but this is a tendon. All right, as always, Fair Use Act, and I'm just commenting on this. Now, this is about iron use and storage in the human body. Now, this is very, very important for the mud fossils. And I'm going to explain to you what happens with the metals in the body. Not specifically iron, but iron is very important. Now, this is by Rachel Cassidy and Regina Frey and Department of Chemistry in Washington. Now listen to this. This is about the different chemicals and the systems in the body. Now it comes down to here and it says the other elements in the body, such as, well, first of all it goes, let's come back to here, I'm sorry. Our discussion of the human body as a chemical system begins by answering these questions. What type of atoms does the body contain? Of the more than 100 chemical elements known to scientists today, only a relatively small number of elements found in the human body. In fact, only 24 of these elements are thought to be essential to the human body. Now, other elements, such as mercury, are sometimes found in the body, but don't perform any known essential or beneficial function. Now, I'm not specifically saying that that's right or wrong. I have no clue, but we're subject to all kinds of toxins. But we do need certain chemicals to exist and to maintain health. Now, let's go on with this here. So, mercury doesn't perform any beneficial function they know of. As a matter of fact, it kills brain cells. But anyway, the largest elemental components of the body by mass are actually oxygen. 65% of your body is made of oxygen. Then you go to carbon is 18, hydrogen 10, nitrogen 3. Now, here's the important part. The other elements in the body, such as calcium, which is your bone material, connective tissues, phosphorus, the same general area, iron, which is your blood, copper, and are known to physiologists as mineral elements and trace elements. Well, there's all kinds of metals in your body. All the metals. There's gold, there's silver, there's every single metal is in your body. And iron, you use a ton of it, yes, but the rest of the things are in trace elements, and yes, they're in your body. Now they taper off to when you get to a very small percentage, but there are other ones in there still in smaller percentages perhaps, but they are still there. Now that is the key. You see these upper end elements, they don't sublimate away. When your body decomposes, it's called sublimation, vaporization. You give off the gases of the body, which are these gases: hydrogen, nitrogen. All right, you give off those gases, they blow off to your body. Oxygen, the oxygen bonds with other things like carbon dioxide. Then also you end up with calcium carbonate, CaCO3. So there's all kinds of things going on in the chemistry of your body. But this is the crucial thing. Iron is a huge thing in your body. And it is in the ferritins of the blood that's in your bones. And that you can see two different types of iron in your body. They're going to be red and they're going to be black. This is how we find out what's inside of mud fossils. Okay, this is truly a fabulous article by Esther Inglis Arkell, and it is about transition metals, and they are not well understood, and they have an extremely important role in life, in the chemistry of life, and they have as much of a role or more in the chemistry of mud fossilization. Now, she talks about best chemists struggle every day to create the molecules you grow in your cells and so forth. And it goes on about, and then it gets down to transition metals. And they're these metals in the middle of the periodic table. Iron is a big one, okay? And then, you've got all your metals in here. Now, what is a transition metal? Well, a transition metal has electrons that you're supposed to fill up all the shells around the nucleus, and they have to be filled before you go to the next level. Well, not in transition metals. They have empty orbitals in the lower levels, and they have very strange capabilities. And here's the capabilities they have. Since transition metals have electrons that link up on both their outer and their inner shells, so they can link up with more than one level on their shells. It's totally different than any other atom. Now, this quality gives transition metals a more complex and varied life than other metals. Now, listen to this. Well, it talks about mixing sodium chloride with water, and you get salty water. Evaporate the water again, and you get sodium chloride again. Now, that's the normal situation, but that is not what you get with transition metals. When you put in a solution, you can drop one element and pick up a better one. Then, more importantly, they say, you can pick up another element, then drop it, then pick up another one. Now that is the key to transition of mud fossils. As they sit in this organic soup, which is the vaporized metals solution, so this is solution over here, when put in a solution, these transition metals, when put in a solution, can drop one element and pick up a better one. More importantly, they can then drop and pick up another element and then drop it and then pick up another one. They want to find the best component to bond to become stable. And when you have blood inside the water that is doing the fossilization, inside of blood there is literally every chemical that exists that the body wants to work with. And that's why you get opals, and the opalization is unbelievable, and the articulation of the tissue layers is stunning. I'll show you that right now. Alright, you can see that's the anatomy of the heart. That's what an anatomist would say a heart looks like. But when you see this tissue here, that's not all the same tissue. There's layers of tissue wrapped in layers of tissue. And there's what they call heartstrings in here that have a certain molecules that they want to attach to. And I'm going to show you what happens in opals, which are fossilized in blood. The blood allows the fossilization to take on every molecule that it desires to take on. Alright, you just saw that an anatomical heart. This is what our actual heart looks like when it gets fossilized in blood, and you can tell the reason is because it becomes opalized. Opal means that it has gotten every single molecule from the blood. I don't care what they say, that's what happens when opal forms. And this is literally a heart. And these are, I believe, what they call the heartstrings. And this is literally the blood has fossilized, the FeO3 blood, the oxygenated blood. These are the ventricle walls. There's a large ventricle and then there's a small ventricle. Some good blood comes in, red blood goes out. I don't know really exactly how the whole thing works, but that is our heart. Alright, I'm talking about an abrupt transition. There it is right there. Those are the tendon fibrils, and they break right off just as flat as a pancake. If they were sticking up out of the ground, that's what you'd see as a flat plateau. And they have all of these the different angles at the top. You can see them if you look at the ones out west. There's another tendon, abrupt transition. Pretty good size. This is how tendon anchors and splays. It anchors up over in this area, if you can see my mouse over here. And then it comes out, and then there's like an abrupt transition, another abrupt transition, and then another abrupt transition over here. That's just the nature of how these things work. They go from an invested area, which is literally glued or tagged in with a bone enthesis. Then they come out until they start to demineralize, and then they get less mineralized, and then they become less mineralized, and then they end up with flesh. I have them here, and I have them in the microscope. Easily seen. Alright, remember I said to pay attention to some of those tendon microscopic shots that we had originally of the living tendon. This is the lower living tendon. You see that? That is the bloody investment layer. This is the calcium layer, which is collagen type 1 is CaCO3. It's calcium carbonates and phosphorus and all that, all the different bone minerals that are in calcium bones and in connective tissues. And these are connective tissues. And this blood glues them together and invests them with first of all, it separates them all, and secondly, it gives them the energy to do what they need to do. It keeps them alive, let's put it that way. And these are all the same age. This is not what this is about. Somebody just carved these a while back. But they're the same from these structures. And if you remember the tendon I showed you, the Achilles tendon, that is the exact same architecture, and these are found everywhere. Those are tendinous materials, and they're Achilles tendons. Here's some more, and the kids play on it. Remember I told you to look at that red slurpy stuff between them? There it is right there. Was blood at one time. And this is an anatomical structure for tendon. You see these? See that rock? That is tendinous material that's loaded. These tendons are loaded. Sometimes they're stretched, but that is a loaded one. Alright, these are shots of living tissue, and remember this style, they're like boards and they have red running between them. That is the synovial sheath, the investment of it. These are like little tiny fibers that Sharpie's fibers eventually, I believe. These are the wavy type. Remember this style here, remember them all. I'm going to show you something else. Alright, that's the Achilles tendon. Remember this carefully. Remember this like architecture. You see that little stripy architecture there? You see this right here? That's what they call an abrupt transition. And that little area there is where it locks in together. And it breaks in a certain exact spot. And they always have to fix them. And there's what they call abrupt transitions. I'll try to show you that too. Alright, this may be a little bit hard to see, but this is the blocky nature of this type of tendon. Well, all tendons have, actually all life has a blocky nature. Now, and it's showing that in this area here, it's all blocky, the whole thing. Now, there's an abrupt transition here that I talked about, and that's this purple area here. There's a ball down at the bottom, and that's the ball that enters here. This is this little block right here that they're showing. And that's where they break. So you have the ball that's normally in the earth, you have a stalk sticking up, and they break right at that abrupt transition, and it is flat as a pancake. So this is stick right up here and squared right off. Alright, I hope I've captured your interest, and if you're interested more, go to Mudfossil University. It's free, there's no charge. Go up there, have a good time, just enjoy it. There's a bunch of videos up there, and go through them and see. If you like what you see, that's fine. If you don't, go play video games, up to you. But this is the reality of life, and it's being ignored by our most prestigious universities. So go up here and learn what's really real, because you're going to actually have to get educated again. They didn't pick up on the fact that life is the foundation of every molecule in the universe. It's just the way it is. Comet 67P was alive. I have a video right here about it. Alright, Comet 67P, it's organic. There's no question about it. I have one right here. See that and this? It's the same thing. So go up there and enjoy yourself, but get some, get into the reality, because the people talking around you are talking about silly things. It's just not true.